Alright, so could you remember any sets of numbers?
Yeah.
Yeah? Which ones could you remember?
Fraction?
Fractions?
Yeah.
Okay. You said rational?
Yeah, I said rational.
Okay.
Fraction.
Then don't agree with me when I
Oh,
say it
I'm
wrong.
sorry.
Alright, rational, what is a rational number? You might know what a rational number is? No?
I'm gonna take a stab at it.
Okay.
Can we divide by something?
Alright,
Or close?
sort of. Yeah, because it can be a fraction. And fractions are really just division. Alright, can you think of any other set of numbers? Anything else? Oh my gosh, I have to remember how wide this stepped off of the foot. Maybe it's just not scooted down. I think that's what it is. Yeah, that's not happening. Alright, what else is there? Anything else? Alright, if you got rational, you're gonna have irrational, right? So irrational. What are irrational numbers?
Can't be that.
Right, can't be divided, can't be a fraction, can't be divided. Be a fraction. Alright. Alright, we're going to talk about all sorts of sets of numbers, okay? And if you have your book, we're going to be going through section 1.1. If you don't have a book, it's not a big deal. I'm going to tell you everything that's in there. You can look it up later if you want. You can watch a video. There's a video online that goes along with section 1.1. You can do the practice homework if you want. How's the assignment coming along? Have you guys started it yet? Mm-hmm. The one that's due September something. The one chapter assignment that you have.
Is it online?
It's on myopenmath.com. Yeah. Alright. So let's talk about just what a set is, okay? Just a set. A set is a well-defined collection of objects. In this case, our selection, we're going to be talking about numbers. That's what our sets will be. Okay? 3 ways to describe a set. One is verbally. One of those irrational sets we're talking about.
They'll stay in here, right?
Yes.
We'll figure it
It's a
out. Does
mine.
she have something?
Alright, so verbal uses a sentence to describe the set. The second way is, the roster method, and you saw this a lot in Algebra 1 when you were talking about functions and not a function, okay? And the roster method, it starts with like a bracket or a brace. Like this. And then it lists each element. And it closes it off. That one's really ugly. And then the last one is that we're going to talk about is set builder. And we'll use set builder a lot. set builder. And it is a combination of verbal and roster. I forgot, somebody wrote on that paper that you cannot read cursive. So I'm going to try to print. Sometimes when I really get to rolling, I'm going to cursive.
Paper.
Not paper, but under paragraphs or things about math. Some people
Oh.
wrote specifically that they cannot read cursive, and if I write in cursive, they're not going to be able to read it.
Yeah, some of them can read.
And I forgot that, but I'll try to print. I remembered about right here. So.
Was that last one, that builder?
Uh-huh. Set builder. Alright, so I'm going to just show you 3 examples. I'm going to move this. Can I move this one? So verbal. All numbers bigger than 12. Okay, bigger than, that would be like, we wouldn't say bigger than, we would say greater than, but this is most of the time we're not going to write a verbal sentence describing it. If we use verbal, that's usually like flippant twins who don't really know their math symbols anyway. Okay, what's the next one? What's it called?
Roster.
Roster. It looks like this. You just list your numbers out. And that's your set of numbers. Do you remember seeing those back when you were talking about functions, domain and range, all that? You're going to see them. Alright, and then the last set of all x such that x is greater than 12. I gotta get this thing moved before I die. Alright, so that's the way we can describe. There's also interval notation. We'll talk about that in just a minute. Let's just talk about the different sets of numbers that we talked about at the very beginning, okay? Can I move these? Can I still write them? Alright.
I just need to find that. Practice.
This thing, yeah, I know. I've practiced for years on that. And you saw how bad the other one was, though.
Mine's afraid to learn.
When I was in high school, I was like, I can never be a math teacher if I can't make those things. And we couldn't even. Anyway. Alright. We've done this before. We've talked about the different sets of numbers before. And we've talked about the history of numbers before. I know we have. You're going to remember it. When we start talking about our sheep herder in the cave, you remember this? He didn't have numbers. Like, there was a time when there was no math homework because there were no numbers, right? So what this guy would do, it's his job to keep up with the sheep. He needs to know if he's lost one. That's how he lived. That's his livelihood. So he slept in this cave. It wasn't really a cave, but it was kind of a cave, in a pen with the sheep. And then in the morning, he would let them out to graze. So when one sheep goes out, he would take a rock and move it to the other side. Okay? And then another sheep goes out, another rock. He keeps up. That's how he keeps up with it. Okay? He can't count. He can't say that's one rock, one sheep. He just knows rock equals sheep. That's what he knows. So then when they come in the daytime, or at nighttime when they come back in, the sheep comes in and the rock that was over here moves over here, right? So what happens if he sees no more sheep, but there's still a rock right there?
And there's still a sheep.
There's still a sheep out, right? That's how he keeps track, because in his mind he cannot count. Okay? Now, that works, but it gets really to be a pain to have to like haul around rocks just to match up to your sheep. So people came up with other ways to keep track, and they would use body parts to count. I mean, think about a kid. When you ask someone under the age of 6, how old are you? What do they do? Do they tell you? Right, they do this. That's what they do. This is natural to us, to do this. This is natural. I have this many. I have this many. Okay? These are natural numbers. And that's actually the set of numbers that we have, the natural numbers. And natural numbers start at 1, and they go up from there. Okay? Those are natural numbers. Put it in a set if you want. That's a set of natural numbers. There were some tribes in South America. This is amazing to me. They had numbered body parts over 100. So like you could say how many sheep you have, and then do like left earlobe. Dang, that's a lot of sheep. Like they just knew each body part had an assignment in order, and they knew that that's how many they had. That's amazing to me. But if you think about it, these are digits. This is what these are called. These are digits. These are digits. So that's not a coincidence, okay? So, all right. So that was great. Okay, that worked out fine. That was well and good for a long time. And then like this earthquake came up, okay? And the earth opened up and swallowed all of the sheep, and he has no sheep left. Do we have a number that represents no sheep at all?
0.
Is it there?
No.
No. So what do these start with? 1. These start with things that occur naturally. And if you think about it, you have to have something in order to count it. It's not natural to count 0. 0 represents an idea. It doesn't represent an amount. And then in this case, that 0 is being used as a placeholder. So it was a really, really long time before the idea of starting over and using 0 as a placeholder. It was a long time in like the entire course of human history before that idea came along. I'm probably going to get this wrong. I think it was an Indian mathematician named Brahmata that first said, we're going to use this goose egg looking thing to represent 0 as a placeholder. I may need to look that up before 7th period, but I'm pretty sure that's what it was. Okay, so then we came up with this idea of whole numbers. And whole numbers start at 0 and then include all the natural numbers. So if you think about this too long, it might make your head explode. This is infinitely big. This is infinitely big. But this is one more. Yeah, put your head around that for a minute. Okay? Now we're going to get out of order as far as the types of numbers that were recognized, but let's jump to you. Now we're exchanging money, okay? And I sold you a sheep for $400, but you only had $200 to give me. So what has happened now? I sold you a sheep for $400, but you only had $200 in your pocket.
I still owe you $200.
You owe me $200. Do I have anything up here to represent you owing me $200? No, we don't. So that's where we come up with this set of numbers, integers. notice there's only one R in that word. It's not integers, it's integers, okay? And integers include all of the whole numbers and their opposite. And I think the first signed numbers, like we had an idea of you owe me something, and I said, yeah, I wasn't there, okay? I know my birthday's a week from today, but I'm not that old. We had the idea of owing something, but we didn't start putting a sign on it, like a plus or a minus sign. I think that happened in about the 1400s during the Renaissance, when trade really became a big thing, and bookkeeping, someone had to keep up with books, because it went from just bartering to actual accounting, like money, give me some gold. Okay, that's what changed things up. There is a set of numbers that's been around longer than integers that we don't have up here. And this is the one that Adrian talked about to begin with, rational numbers. Like, there have been fractions pretty much as long as there's been numbers. Because even in the Bible, the first laws that were laid down, you had to give a tenth of your crops, or a tenth of your whatever, in a sacrifice. So that's, some of our earliest recordings, a tenth is a fraction. A rational number isn't just a fraction, though. A rational number is anything that can be a fraction. I'm going to define that instead of giving it a set, because I want us to talk about it. Notice it's can be. It's not that it has to be, right? It can be a fraction. 7 can be a fraction. Just put it 7 over 1. So every number that we've talked about up to this point is a rational number. All of them can be fractions. Okay? Now, my favorite story, probably math story, is about these irrational numbers. Irrational, like we wrote for our bell ringer, can't be fractions. So you remember that guy, Pythagoras? Remember him? What do we know about Pythagoras? When you hear Pythagoras, what do you think? Pythagorean theorem. Yep. Okay. So Pythagoras is like a really weird guy, and he started this religion, the Pythagoreans, and they studied and worshipped numbers. That's what they did. Okay. Like, they felt like there were some numbers that were perfect, and some numbers were better than others. And in their idea of perfect numbers, there was no such thing as an irrational number. Because that just didn't fit with their idea of perfection of numbers, okay? It didn't fit. And it, got vicious, right? People died within this society, like they would be killed because of this rational, irrational thing, okay? But here's what I love. The Pythagorean theorem proves the existence of irrational numbers. If you remember Pythagorean theorem, you have a triangle, okay? If this is 3, and this is 5, 3 squared is 9, 5 squared is 25, 9 plus 25 is 34, this is going to be whatever the square root of 34 is. Square root of 34 is an irrational number. So this theorem, named after the dude who started the religion, actually ended up destroying his religion. That's irony. Hollywood needs to make a movie about that. That is a picture of irony. When Miss Cole asks you for an example of irony, tell her that story. Once you start talking about math, you're just going to get an A. She's going to be like, okay, yeah, sounds good. You'll get an A. All right? So next time she asks you about, but that truly is irony. This theorem that proved irrational numbers destroyed the religion that he founded. And that's what we know him for the most. I love it. It's fantastic. There's fun math stories. You just don't get to hear them. So all of these are real numbers, okay? All of these are real numbers, even the irrational one, okay? You will remember we do have imaginary numbers. Remember the complex numbers? We'll talk about those more later. But we do have complex numbers or imaginary numbers. Okay, there's another way to write out a set of numbers, and that's using interval notation. Okay, interval notation uses hard brackets or soft brackets. It looks like a point, okay? Hard brackets mean the endpoints are included. Soft brackets mean they are not included. Let me show you what we're talking about here. Alright, so this is my set of numbers between 3 and 8. Closed circle on 3 means that 3 is included. Open circle on 8 means that 8 is not. This, in interval notation, would look like this. It starts at 3 and includes 3, and it ends at 8 and does not include 8. That's what that looks like in interval notation. In set notation, this is an interval. In set notation, all x such that 3 is less than or equal to x, which is less than 8. Interval, set. There's a really good chart in your book on, where are you going? On page 13. In the PDF, it's page 13. In the actual book, it's page 3. It's the 13th PDF, but it's page 3 in the book. And it's a really good chart of set notation, interval notation, and then a matching number line. I encourage you to look over that chart on page PDF 13 of the book, page 3. Okay, can I move this? All right, let's look at intersection and union. So suppose A and B are two sets, okay? Oh, there's that cursive again, sorry. What does what mean? Okay, see in your book, this is the book I'm on. Is this what you're asking about? It's both. If you're just scrolling through the PDFs, it's page 13. But if you look on the book page, it's page 3. But it's the 13th PDF, because the PDFs include like the title page and the different content, all that stuff. So that's why I'm giving you both. Alright, so suppose A and B are two sets. The intersection of A and B would look like this. A, and then this upside down U, B. That's when you see this, you think the intersection of A and B, okay? out the door?
No.
Okay. All right, the intersection of A and B is x such that x is an element in A and x is an element in B. It has to be in both of them. Okay, it has to be in A and B. That's an intersection. A union. Alright, so the intersection is an and. What do you think a union is? An or. And it looks like a U. X such that X is an element in A or X is an element in B. You get that written, I'll show you an example. But I'll let you get that written. Alright. Let's say that A is, I forgot it. Hang on. One, two, and three. How could I have forgotten 1, 2, and 3? And B is 2, 4, 6. Okay. So A with an intersection of B. Intersection means it's an and. Think of it like this. And, just look. A and B. Just imagine that's an N, okay? It's not. It's an upside down capital U. Just imagine that's an N. A and B. What's an A and B? What's in A and B? What's in both of them? 2. So that's the only number that's in the intersection. That's it. But if I said A as a union of B, that's an OR. What would that be? It's got to be in one or the other. So that's going to be 1, 2. I'm not going to write 2 twice. Has to be in both of them. It's only 2. If I don't care, I can pick any of these. Okay? You remember those Venn diagrams that you used to do? These are kind of like a Venn diagram. Okay? You could do, that's A, that's B, N. 2 is 12, 4, and 6. Where is their intersection? They intersect at 2. See, they're literally intersecting at 2. And then if I wanted to just join them together, if I wanted to have a union, it would include all of them. I'm joining them together. Okay? Alright, do you have any questions about sets of numbers or what we're calling them or anything like that? Alright, we're going to stop there for today. Okay?